There we go. Okay, great. So let's go ahead and get started. Are there any questions from the early couple of sections from chapter 4? We talked about sort of the properties of water, really, and solubility, and then we looked at precipitation reactions yesterday, the net ionic equation in particular. Any questions on that?
I have a question.
Mm-hmm.
This is Erin speaking. You said the other day about the A columns having charges or negative charges. What about the B column?
The B columns, what it is they're variable. They're variable. So what can happen is, like if you have, for example, iron sometimes is +2, but sometimes it's +3. And so in general, you can't, you don't know which one it is. You figure it out from context. So for example, let's say you had this. If you saw this formula here, you'd say, oh, well, I recognize this one is 7A, so that's -1. And there's 2 of them, so 2 times -1 is -2. So then you'd say, okay, we have to have a neutrality. So that means this one's got to be +2, right? Whereas if the formula were FeCl3, now you'd say it's 3 times -1. So that means this one's got to be +3. So yeah, so the B elements, there's no, I mean, there are you can really get into the nitty gritty and find certain regularities in them, but it's not worth the effort.
Okay, thanks.
You're welcome. That's a good question. It would be nice in a sense if the chemistry of those B elements was more regular, but if it were more regular, that would probably end up sort of limiting the possibilities, the flexibility of these elements to do their chemistry, and that would make our reality a little more limited, right? So the fewer possibilities you allow in nature, the fewer possibilities you have for variety, right? So the chemistry of those elements are used in biochemistry, right? So iron, for example, is an element that's in myoglobin and hemoglobin, and it's sort of specific, peculiar chemistry is what allows myoglobin and hemoglobin to transfer oxygen back and forth and that sort of thing. Okay. All right. Any other questions? Okay, so what I want to do today, we looked at precipitation reactions yesterday. I want to look at acid-base reactions. And what we're going to do is we're going to look at, I would call it an introduction to acid-base chemistry. We don't go into it in great detail in this course. We go into acid-base chemistry in great detail in the next course, Chem 1200. And then you use that kind of information when you move on to things like organic chemistry, acids and base chemistry. So really what we're going to do here today is look at sort of the, what is an acid? How do you identify an acid? What is a typical reaction of an acid? And then we'll give you a little bit of info about a sort of second level definition of what an acid is. Okay. So the first thing I'm going to do, and again, I'm going to try to base this on the ALEKS problems because I think it's a little more direct for you. So what I'm going to do first is look at identifying acids and bases from their formulas. These are the chemical formulas. Okay, so the first one is H2SO3, and then we have KBrO4, and then we have H3PO4, and then we have HCl. Okay, and then what we're going to do is we're going to classify these as 4 different substances. The first one is ionic. The second one is molecular. The third one is acid. And the fourth one is a base. So those are, in a sense, our 4 categories of materials, right? So if I say, here's a chemical, is it, what kind of chemical is it? You would say it's either ionic, molecular, acid or base, right? Okay. So here's, it's not full, there's no foolproof method. It really, a lot of it comes from just your experience working with these substances, but here is one approach to this. When you look at the chemical formula, if you see that there's a hydrogen followed by something else, okay? So for example, HA or HB, typically that's an acid. Typically that's an acid. So for example, if I were to show you HNO3, we're sort of, you know, piggybacking on, we're building on what we talked about yesterday in terms of ionic, in terms of binary compounds, two parts, right? So if you have a hydrogen attached to something which is typically negatively charged, then you have an acid. So HNO3, that would be your polyatomic ion, right? Polyatomic ion. That would be, typically that would be an acid. Another example, now it could be more than one hydrogen. So for example, you could have H2CO3. So even though there's two hydrogens, it's still a hydrogen in front of the rest of the compound, rest of the formula. So again, here's another polyatomic ion. That's the carbonate ion. Okay, so hydrogen polyatomic ion, that would be an acid as well. You can even have three. So you could have H3ASO4, for example, hydrogen polyatomic ion. And it doesn't have to be a polyatomic ion, it could be a monatomic ion. So it could be, for example, HI. So there's your hydrogen, and then there's your anion, right? And so again, that would be an acid. So typically acids are the ones that follow that format. So if we look through all four of these, there's three of them that meet that criterion, right? So you look at this one here, there's hydrogen, polyatomic ion, hydrogen, polyatomic ion, hydrogen, monatomic ion, right? So those all fit that classification of an acid. So we could say, hey, those are all acids right there. Okay. And then you take a look at the, let's look at bases now. Make a little room for myself over here. So let's look at bases. Now, there are two categories of bases. The first one are the metal hydroxides. So if you have any of these metals, this is group 1A, right? We were talking a lot about group 1A, Aaron's question about that issue of the groups. So this is group 1A. And then you have the second group, which is beryllium is usually not included in this. Magnesium, calcium, strontium, and barium. If you have any of those metals attached to hydroxide, so the key of a base is you're talking about what's called the hydroxide ion. Okay, that's the OH minus. You have a base. So for example, now hydroxide's -1, lithium in group 1A is +1, right? So if you have Li, OH, it actually follows the same kind of rules of charges that ionic compounds have. The positive has to balance the negative. And since the hydroxide is -1, right, that's -1, the metal is going to be +1, right? The first column, they're +1. So that would be a base. It has one of these 9 metals, right? It's just those 9, actually. It's one of those 9 metals with a hydroxide. Same thing if you had, for example, potassium hydroxide. You have one of those 9 metals with a hydroxide, okay? Now, if you have one of the second metals, you know, the group 2A, right? This is 2A, this is 1A. If you have group 2A, the charges of the group 2A metals are +2, so you just need 2 of the hydroxides to balance the charge. So if this is +2, you got to have 2 hydroxides, right? Just because each one is -1, 2 of them would be -2, that would balance your +2, okay? So that would be a base as well. And that's really the first category of bases, are these 9 metals attached to either one hydroxide, right? So here it's going to be 1 hydroxide. If it's in the second column, it's going to be 2 of the hydroxides. I'll write it this way, OH2 in parentheses. There we go, okay. And those would be the bases. If you have a different metal, it's not a base. So for example, if you have iron, that's a metal. And if it's combined to 2 hydroxide, it looks like, hey, that looks like a base, right? It has the same kind of format, but be careful. Unless it's one of these 9 metals, it's not a base. This would be an ionic compound. Okay. And the reason actually has to do with the solubility guidelines of all things. What happens is hydroxides are generally not soluble. They don't dissolve into water, so they don't form electrolytes. So iron hydroxide just doesn't dissolve. It'll just fall to the bottom of the water like a rock. It doesn't dissolve. However, group 1A and group 2A compounds are soluble, right? They're always soluble, particularly group 1. And so what happens is those hydroxide ions get dissolved into the water, and now they form hydroxide. And that's really what makes a base, is whether it forms hydroxide in the water. Okay. So in a sense, bases are electrolytes, right? They're a type of electrolyte. Lithium hydroxide dissolves into lithium ions and hydroxide ions, and you have electrolytes, okay? So if we look through here, we don't see any compounds that sort of fit that format, right? There's nothing in there of like KOH or SROH2, none of those in there. So it doesn't look like there's any bases in there. But I do want to point out there's a second type of base, and those of you that are studying biology, you're aware of these kinds of bases, and those are what we call the nitrogen bases. And this is a topic that we really get into in Chemistry 1200 because it has a lot to do with pH. Nitrogen bases are typically compounds in which a nitrogen atom is bonded to 1 or more hydrogens. Okay, so here's an example. A nitrogen is bonded to 3 hydrogens, or some combination of hydrogens and carbons. Okay, so in this particular case, the nitrogen is bonded to 2 hydrogens and 1 carbon, or it could be a nitrogen bonded to 2 carbons and 1 hydrogen. Sorry, that carbon's not coming out very well. Any combination, 3 hydrogens, no carbons, 2 hydrogens, 1 carbon, 1 hydrogen, 2 carbons, no hydrogens, 3 carbons, right? So any combination of carbons and hydrogens, as long as there's 3 of them, right? So as long as you have 3, that would be called a base, okay? And so the reason for that is that, let me actually just go ahead and save this, and then I'll come back to it. The reason that those are bases really gets down to the nitty-gritty of what a base is. So if you take sodium hydroxide and you dissolve, sodium hydroxide is a solid. It's just a white pellets, little white pellets. They look like little tablets. If you dissolve it in water, it becomes electrolytes. And it's very soluble. So it forms a lot of electrolytes. So this is what we would call a strong electrolyte. Remember at the beginning of the chapter, I kind of briefly mentioned that electrolytes are little particles that conduct electricity. So sodium hydroxide, if you were to dissolve it into water, would conduct electricity really well. There's these nice little experiments you can look up on YouTube. You just type in strong electrolyte light bulb, and you'll see that you can stick a light bulb into it and it lights up like crazy because there's conductivity, these strong electrolytes. So these bases are strong. Well, it turns out the nitrogen bases are also bases, but they're not as good at conducting. So we typically call them weak electrolytes. So one example is ammonia. Ammonia is, I guess, is a liquid. And if you dissolve it into water, here's what will happen. It will break up, and we'll talk about this a little bit later, into two ions. It'll react actually with the water. And you get these two ions. So see how you get the hydroxide? That hydroxide is the same hydroxide we're talking about right there. And that's really what our definition of a base is. If you put it into water and it forms a hydroxide ion, we call that a base. Iron hydroxide, because it doesn't dissolve, it doesn't form any hydroxides. So it's not a base, right? So these nitrogen bases are actually bases. So for example, amino acids, even though amino acids are considered acids, in a sense, there's a basic part of the molecule. So an amino acid has a hydrogen. It may have some other group like a CH3 group. It has a I'm going to write this kind of backwards, COOH group. That's what actually makes it an acid, is that hydrogen. And then typically it has an NH2 group here as well. And so look at that nitrogen. It's bonded to two hydrogens and it's bonded to a carbon. So that's actually basic. It's actually a base right there. So amino acids are interesting molecules in that they're acids, right? Got the hydrogen and then the negative charge. And then you've got the base with the nitrogen as well. Other compounds that you're familiar with, these natural products, right? Many of the natural products that we've heard of that have an effect on the brain are actually bases. So for example, caffeine, right? Caffeine is pretty powerful drug that people ingest pretty much every day, particularly people involved in college. Caffeine, morphine, right? That's another example of one. I have a little mind problem here. What's the nicotine, right? I was thinking tobacco, nicotine. Nicotine is another example of these. Cocaine. Those are all examples of these nitrogen bases, right? And the reason they're nitrogen bases is because there's a nitrogen in a ring, which is attached to carbon atoms. And so right there, typically you'll have a hydrogen here as well. You've got this nitrogen. So let me just show you sort of a generic. There we go. 5 carbons and a nitrogen, right? We won't worry about the bonding and the other groups on the molecule, but there's your nitrogen in there, right? And it's attached to 2 carbons and a hydrogen. And so it will do the same thing. If you dissolve it into water, it'll form hydroxide ions, okay? So there's 2 groups of bases. Now going back, we went and we looked at these 4 compounds and we said, hey, there's nothing there with a hydroxide, so it's not a base. But to be complete, we would need to be thorough. We would need to go back and look and see if there's any nitrogen bases in there as well. Is there anything like NH3? Is there anything that has carbons with a nitrogen? Nitrogen with hydrogens? There's nothing in there like that. So definitely we can, say, look, in those 4 groups, there are no bases. We're clear on that one, okay? So far we've got 3 acids and no bases, and then we've got this substance over here, the KBRO4. So the only issue is that it could be ionic or molecular, and here's how you tell. You look at the formula, see how it's got a metal? Ionic compounds are famous for having metals, and it's not the case that all ionic compounds have metals, but the vast majority of them do. So if you have a metal and then you have something that's not an OH, right, that means it's an ionic compound. So right there's our ionic compound, okay? So it looks like for this particular one, the only issue here is how do we define molecular compounds? So acids, in a sense, are molecular compounds, okay? So in a sense, what you would do is you would say, look, if something is an acid, it is by definition a molecular compound also. So anything that's an acid is also a molecular compound, okay? That just has to do with, a definition of what it is. Let me show you one more example. Okay, so this one has a different set of compounds. And then again, our categories, let me come back so I can see in case someone comes in. Our categories are ionic, molecular, acid, and base. Okay, so let's look at the first one. First one, very clear it's a base, right? You've got one of the group 2A metals. So that's a group 2A metal with hydroxide. And it actually follows the kind of format that we talked about. If it was in group 2A, it would have 2 hydroxides. So there's your base right there. That's a definite base. Second one has the hydrogen with a polyatomic ion. And remember, an acid is a hydrogen with either a monatomic ion. Remember, monatomic just means one atom. So chloride or bromide or iodide, or a polyatomic ion, phosphate. This is not one of the polyatomic ions that I went over last week. This is phosphite. Phosphite. It's not a very common acid, but you can still see it's got the form of a polyatomic ion. So that's hydrogen with a polyatomic ion. So that's an acid. But again, an acid by definition is also a molecular compound. So you're just going to click off both of those. Okay. Third one. It doesn't look like it's a base, right? It's a group 1 metal, group 1A, but it's not with a hydroxide. So if it's a metal and it's not a hydroxide, that just means it's an ionic compound. And then the last one, hydrogen polyatomic ion. That's an acid, right? So hydrogen with a polyatomic ion, and then it's molecular also, just by definition. Acids are molecular compounds. Okay. And there you go. So that's, in those two examples, they didn't get, so let me give you one. Suppose I said CH3 NH2. Okay, so for that one, notice you've got a nitrogen and it's bonded to hydrogens. That's a giveaway right there. Nitrogen to hydrogen. That would be a base. Okay, because it's one of those nitrogen bases. And then just to be complete, if it's nitrogen with hydrogen or carbon, see those are all nonmetals. See how everything in there is nonmetal? Carbon, hydrogen, nitrogen, those are all nonmetals. That's really what a molecular compound is. It's when none of the metals are in there. So this would also be molecular. So if you do have a nitrogen base, I'll just kind of make a little note here. Nitrogen bases are also molecular, just as acids are molecular. Okay, and there you go. So that's kind of cool. That's sort of a fun problem. Okay, so let's take a look at writing some equations here. So just as we wrote equations for precipitation reactions, we can also write equations for acids and bases here. So this one is called predicting the products of a neutralization reaction. Okay, so here all they're going to ask you to do is to predict the product. So they're going to give you the formula for the reactants. The states of matter are not given, so I won't worry about those. And then they just want us to give the products. Okay, so in general, a neutralization, that's another term that we use that essentially means acid base. Technically, they don't mean the same thing. Neutralization means that one thing is counteracting the other, right? So you're neutralizing it. And you can have neutralization reactions with other types of reactions, but typically these days, Neutralization means acid-base chemistry. So an acid-base reaction, just in general, is what you get is you take an acid and you react it with a base. And often, I'm not going to say always, but very often what you get is what's called a salt. And then you also get water. Okay, that's a typical format for a neutralization reaction, is an acid plus a base gives you a salt plus water. So what we call table salt, sodium chloride, halite, is actually a product of an acid-base reaction, right? So when you pour out salt, you're actually pouring out the product of an acid, of a neutralization reaction. Some acid, sodium hydroxide, reacted with some base, hydrochloric acid, for example, and that acid other way around. The acid, hydrochloric acid, the base, sodium hydroxide, react to form water plus sodium chloride. So sodium chloride is the salt that's formed. So we can also kind of reverse it. We can go backwards and say, hey, what is a salt? If someone ever asks you what's a salt, what is a salt? A salt, outside of our everyday context of meaning sodium chloride, a salt is a product of an acid-base reaction. That's what a salt is. Okay, so you can kind of do it either way. Hey, what are the products of an acid and a base reaction? Oh, a salt and water. Or you could say, what's a salt? A salt is a product of an acid-base reaction, water being the other one. So typically, most of the ones that we look at in here, again, how do we recognize an acid? We have two parts. You have the hydrogen and the polyatomic ion in this case. So that's clearly an acid, right? And then for the base, you have a group 2A metal, and then you have hydroxides. So that's a base, right? So we can identify that. Here's the way that I do it. Again, remember we talked about precipitation reactions were what we call double replacement. So precipitation reactions were like that. Well, so are acid-base reactions. Not always, but very often they are. So for this particular type of problem, they are. So here's the way you deal with it. Remember what we said? You take the first part of one of the reactants and you combine it with the second part of the other reactant. So in this case, you're combining the hydrogen with the hydroxide. And then you take the first part of the second one and you combine it with the second part of the first one, right? So this would be barium and perchlorate, okay? So let's just be careful about this. So what you would do then is you'd say, hey, what do you get? You get H and OH. So let me just point out that if you have H and you have OH and you combine them, we generally don't write it that way. We generally write it as H2O. That would be H2O, right? HOH is really H2O. So I'm taking the H and I'm taking the OH and I'm getting H2O. So there's one of our products, right? There's the water. What about the other one? We take the barium and we combine it with this other ion, the polyatomic ion called a perchlorate. Okay. Now here's where you have to be very careful, however. The issue here is that when we have an acid, the hydrogen that's in the acid has a charge of +1. And the way you can remember this is hydrogen is actually in the same column, group 1A, as the alkali metals. So they're all +1 because they're all group 1A. So for acids, hydrogen is actually +1. So if the hydrogen is +1, that means the perchlorate's got to be -1. So you don't have to remember that perchlorate is -1. You just have to remember that hydrogen is +1 and then figure out the perchlorate from it. So that means this is -1. But what about the barium? The barium is in group 2A, right? That's all the way over here. So that's in group 2. So that's +2. Okay. So that means you got something here that's +2. So that means you got to have 2 perchlorates. You got to have a 2 there, right? Because if this one, if the metal is +2 and the non-metal is -1, they have to balance. So you have to have 2 of them. So that means that, well, we've written the products. So in this particular problem, let me just come back to it. It says, make sure the equation is balanced. I just want to be careful about that. Make sure you balance it. So we've written the 2 products. So here's your salt. Doesn't matter which order you write. You can write the salt and then the water, or the water and then the salt. You have your salt here. There's your water, okay? It's not balanced, however, so we do need to balance it, okay? So it's up to you how you want to balance it. The way that I balance it is I look for polyatomic ions. So see how that's a polyatomic ion there? And there's 1 polyatomic ion, 1 perchlorate. Look how there's 2 perchlorates over there. So instead of balancing chlorine all by itself, I just balance the polyatomic ions. But you could just do it based on chlorine as well. So 2 chlorines or 2 perchlorates. So you need 2 perchlorates over here. That 2 will make this a 2. Okay. So that's not so bad. We got the perchlorates balanced. Now let's see if everything else is balanced. The bariums are balanced. What about the hydrogens? You've got 2 hydrogens here, and then you've got another 2 here in the hydroxide. So that's 4, but you've only got 2 hydrogens over here. So just put a 2, and then that'll balance it, okay? So I balanced the perchlorates, and then I balanced the hydrogen, and that should work pretty well, okay? Let's take a look at another one. So for this, you're writing the equation, you're writing the products, and then you're balancing it. So let's take a look at another one. Here's one. This one is not difficult to balance. There's no balancing with this one, so it's a little easier.
Question.
Yeah, go ahead.
What happens if someone does an experiment with like unbalanced elements? It wouldn't work?
That's a good question. So nature's going to do what nature does. What happens is when you mix things together, they're going to react based on how much is there, right? So for example, imagine that, here's like kind of a cartoonish type example. Imagine that your body's trying to produce hair, trying to grow hair, which is mainly keratin, right? And you just don't have enough of the amino acids to make that protein. What it will do is it'll just make a little bit of hair and then it'll stop, right? Your hair will just stop growing. So so the balancing is something we do to figure out how much we have to put in so to get the maximum amount out. So balancing is something that nature does kind of on its own. And then we figure out what that equation is and we balance it just so that we know how much to mix together. So let's say that we had that previous reaction. Let me just save this one and come back to the one that I just did. Suppose I said, okay, because this is the ratio that has to happen for it to work. Suppose I didn't balance it. And I thought the reaction was just like this. What would happen is I would say, oh, I just need to put in the same amount of this as I need to put in this. So I put them in, and then what would happen is you get half as much out as you expected. You just get less. So then I would say, well, what's wrong? Like I expected to get this much out and I only got half as much as I expected. And then you go back and say, oh, I see what happened. I didn't put enough of this in there. I need to put more of this. I need to put twice as much as I put in. So it'd be kind of like you said, hey, I'm going to make a cake and my formula is 1 cup of flour and 1 cup of sugar. And what would happen is, I guess it would be too sweet, right? If you put in 1 cup of flour and 1 cup of sugar, it'd just be too sweet. So you'd say, oh, it didn't come out very well. So then you'd go back and you'd look, oh, I do 2 cups of flour and 1 cup of sugar. Now my cake came out okay. So it would still happen. In the laboratory, the reaction would still happen. It's just you would get less than you expected to get.
Okay. Thanks.
No problem. It's a good question. Okay, so here's the one that I want to look at now, which is it's the same acid as HClO4, which is perchloric acid. And then we have another base here, right? So recognize hydrogen polyatomic ion, that's an acid. Group 1A metal, hydroxide, that's a base, right? So it could be group 2, it could be barium hydroxide, like the one that we just looked at, or it could be group 1, sodium, potassium, acid base. So that means we already know that we're going to get a salt in water. So you actually, technically, you already know you have H2O, right? But here's what happens. The hydrogen combines with the hydroxide, and that's going to give you water. Okay? And then the metal is going to combine with the polyatomic ion, so that's going to be the K with the ClO4, and that's going to give you the salt. And then you say, well, what about charges? Let's go through the charges here. The charges, I mean, really all of these acid-base reactions and precipitation reactions are all about charges. You know, in chemistry, just sort of think about it. There are two qualities of matter that we are generally concerned with. One is mass, how much something weighs, right? That was the whole chapter 3 was really about mass. The second is charge. When you think about like how cell phones work and how all of our modern materials like plastics and conductors and insulators and semiconductors, there's two properties of matter that we look at. One is how much mass something has. So for example, if you want to make a battery, you want the battery to be light. You don't want a heavy battery, right? So that's why these new electric cars are not using the battery technology that was invented the last century. Those batteries use lead, and lead is very, very dense. So it's heavy, right? So if in a modern electric car used a lead battery, it'd be very heavy and very fuel inefficient. So what do they use? They use lithium. Lithium is very light metal, right? It's one of the lightest metal. It's actually less dense than water of all things. So really low density. So lithium would be good. So that's mass. But the other property is charge. Remember, a battery is conducting electricity. It's producing electrons to do electrical work. So charge is the second thing. So really what we're going through here, chapter 3, we did mass. Here, really what we're doing is charges. So let's evaluate these charges. Hydrogen is +1. And so if you look at this formula, HClO4-, in order for that to balance, they gave you the formula. So if it has one hydrogen and that's +1, that means the perchlorate's got to be -1. Okay, so we know what that charge is. Now we come over to KOH. Potassium is in group 1A, so that's plus. And then we already know, hey, the hydroxide ion, that's a famous ion. That's one we have to know. That one's -1. So everything is balanced there. So actually, take a look, +1, -1, that's balanced. Now the water, generally we write it as H2O, but in a sense, you can think of water, we wouldn't write it this way, but you can think of it as +1, -1. The hydroxide is -1 and the hydrogen is +1. But again, typically we write it this way, but it is in a sense +1 and -1. So what do we have? We have a balanced equation, right? If you think about it, you've got the same number of hydrogens, 2 on the left side, 2 on the right. You've got 1 chlorine on both sides. You've got 4 oxygens plus a 5th one, 4 oxygens plus a 5th one, and then you got 1 potassium on both sides. So it's balanced right there. So sometimes equations are balanced just by writing the products out. Okay, there you go. Let's see. Good. I'm just going to kind of scroll through here just for 1 minute, just to see if there's any that are significantly different than that one, just to see if there's any where they throw in a nitrogen base. I don't want to not talk about nitrogen bases if they're going to have you do that one. Okay, looks like it's just those ones. Okay, so no need to worry about nitrogen bases at this point. Okay. Okay, so the next issue is identifying reactions in terms of determining what type of reaction they are. And so it's actually kind of fun. It's classifying. And so if you like classifying things, it's kind of fun. So let me show you an example here. So this is called identifying precipitation, combustion, and acid-base reactions. Okay, it's not that hard, but it's very easy to make mistakes on it. So let me show you an example. So here's HBr plus NaOH goes to NaBr plus H2O. And then the second one is 4K plus O2 goes to 2K2O. And the third one is Na2S plus FeCl2 goes to 2NaCl plus FeS. And then the last one is Na2CO3 goes to Na2O plus CO2. Okay, and then you have some possibilities. So, so let me write these possibilities here. A is what's called combination. B is what's called single replacement. C is called double replacement. D is decomposition. E is precipitation. F is combustion. And then G is acid base. Okay. Let me make sure I've got all of those. Okay, good. All right, so let's go through these and see if we can identify what these are. Now, one thing to point out is that a reaction can be more than one of these categories. So it can be, for example, precipitation is also double replacement. Okay, so let's take a look at this one. So here, this looks like an acid, right? Hydrogen with a monatomic ion. Sodium hydroxide, so that's your group 1A metal with a hydroxide. So that's acid base. So if it's an acid reacting with a base, that's an acid base reaction. So we look through here, oh, there's G, okay, so that's acid base. And again, take a look at the products. You got a salt and you got water. So that's definitely an acid base. But it's also, remember, one part with, an acid-base reaction is also hydrogen with hydroxide. That's what gives you the water. And it's also sodium with the bromide. So it's also double replacement. So we put a C there. Okay. So acid-base reactions are both of those. The second one, now with this one, take a look. It's just potassium. It's just an element. One thing to point out, when you see elements reacting with each other, so just an element, not a compound, right? It's just potassium or just oxygen. Those are not precipitation or acid base. An acid base and a precipitation reaction are both double replacement. So if you just have an element, there's no double, there's no two parts. Both reactants have to have two parts for it to be double replacement. So there's no way it can be double replacement. So what you do is you say, okay, so we know it's not acid base, we know it's not precipitation, we know it's not double replacement. What's left? Well, if you have an element and an element, and now you're forming a compound. So if you have, I'll just write E for element, E for element. If you have two elements reacting with each other They're forming something more complicated, right? Two simple things are forming something more complicated. That's called a combination, okay? So simple plus simple complex, that's a combination. So that would be F. Okay. The third one, take a look. You've got two parts here, but that part right there doesn't have a hydroxide. If the second part were hydroxide, that could be a base, but it's not. Second reactant here, metal with a nonmetal. So those are two parts. And then if you look at it on the product side, you've got two parts as well. So that is a double replacement, but it's not an acid base. So you say, okay, well, what about the states of matter? So for this one, I'm going to go through and show you. They give you the states of matter. And they tell you these are aqueous, 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 and then solid. So in that third one, if you look at it, what do you got? Two aqueuses on the reactant side, one aqueous on the product side, one solid. That's a precipitation, right? You're precipitating, you're forming a solid out of these ionic compounds. So it's a double replacement and it's a precipitation. So for that one, it would be E and it would be C. So let me do C and E actually. Okay. And then the last one, let's look at the last one here. If you look at this one, it's a compound and it's breaking up into two smaller compounds, less complex. Okay, so this is the reverse of a combination. If you take two simple things and you form something that's more complicated, that's a combination reaction. If you take one thing and you break it up into two simpler things, that's a decomposition reaction. So there should be a decomposition, there it is, D. So that would be a decomposition reaction, okay? And I'm gonna show you just one more, just to kind of play it all out here. One more reaction would be like this. CH4 plus 2O2 to form CO2 plus 2H2O. Okay, that one's the one you want to recognize. If you have carbon and hydrogen, this is called a hydrocarbon, and it reacts with oxygen, hydrocarbon plus oxygen, that's called combustion. Okay, so that's a combustion reaction. So if you saw that one, you would put down that that's, oh, I made a mistake here, didn't I? I'm sorry. I put F here. Why did I put F there? F is A. Thank you. I don't know why I put F there. Very good. Your comment was exactly right. I just noticed that myself. I don't know why I put F there. So simple plus simple, more complex is a combination. So I circled A. I don't know why I put F, but whatever. So anyways, the combustion is when you have a hydrocarbon and you have an oxygen, those two together, that's combustion. So this one would be combustion, which is F. This one's F, okay? Okay, so simpler plus simpler, more complex, that's combination. More complex into simpler plus simpler, that would be decomposition, right? They're the reverse of each other. Good. All right, let's head over. And okay, so what I want to show you now is predicting the products of the reaction of a strong acid with water. So predicting products from the reaction of strong acid with water. So this is where acid-base chemistry gets interesting, to me anyways. Okay. So in general, when we think about acid-base chemistry, we think of an acid, right? Hydrogen with some polyatomic or monatomic ion reacting with a base, group 1A or group 2A metal with a hydroxide or a nitrogen base, right? In fact, acids and bases are more broad than that in nature. And so it's often the case that we talk about acid-base chemistry from a more sophisticated perspective. And this is that example right here. So what happens when an acid just dissolves in water? We typically write it like this. This is called the Arrhenius Model, or the Arrhenius Theory, is that if you take an acid like HNO3, you dissolve it into water, right? That's dissolving when we write the water, next to the arrow like that. What we generally say is, oh, what happens is the water pulls the ions apart and you get two ions like that. That's called the Arrhenius theory. And that's a common way of describing what an acid is. You put it into water, it forms H plus and it forms NO3 minus, for example. But in fact, what we now know is that that's not what really happens. It turns out what happens is the water actually reacts with the HNO3. So acids, they don't really dissolve into water. They react with water. So that's one thing that was determined in the 20th century as opposed to when Arrhenius was around in the 19th century, is that it's actually more interesting what's happening. The water is actually reacting with the acid. And so generally, this is how we think about it. I'm going to show you a little picture here. I'm going to write the formula out for the HNO3. Oops. And then I'm going to write out the formula for the water. Okay. Here's what happens at the molecular level. This hydrogen is transferred from the acid to the water. So it gets knocked over to the oxygen. It goes over like that. They collide with each other. It's a physical collision. It's not like it's flying through space. The two molecules collide and is transferred. The hydrogen is transferred. So after that process is done, what happens is the nitrogen still has all the oxygens, but it doesn't have the hydrogen. And then the oxygen in the water now has 3 hydrogens. However, it's not a hydrogen atom that gets transferred, it's a hydrogen ion, so it has a positive charge. So what happens is that positive charge is transferred to the water with the hydrogen. So the whole thing has a charge of +1. So it's all positively charged because it's H plus that's moving over, not H. Likewise, if the oxygen over here next to the nitrogen loses a positive charge, it now becomes negative. So this is negative over here. And the way we write the chemical formulas is like this. You write it as NO3 minus, and you write this one as 3 hydrogens, so H3, 1 oxygen, O, and then it has a positive charge. And this is called the hydronium ion. So in fact, HNO3 going into water doesn't really produce H plus and NO3 minus, although you will see it written that way. What it really does is it forms NO3 minus, so that's the same, but it also forms this H3O plus. And this is called the hydronium ion. Okay, so how do we deal with that? How do we write these equations without going through all that analysis? It's very simple. You recognize you've got an acid, and if you have an acid with water, the acid will transfer the H plus to the water. So acid, if you know you have an acid, it will transfer H plus to the water. And so water, if you give it an H plus, is going to give you this one, hydronium ion. So you know right there, an acid with water will give you the hydronium ion. So you know that product right there. The other product, all you got to do is just take what you started off with and then just figure out what that negative ion is. The nitrate ion, for example. That's going to be your second product. Again, it doesn't matter which order you write it in. You could go H3O plus NO3 minus, or you could do NO3 minus plus H3O plus. But an acid with water will definitely give you a hydronium ion. And that's a different way of looking at acid-base chemistry. And it's actually the way that we look at it in Chemistry 1200 when you take the next course, if you take the next course. So let me show you another example. Let me see if I find one that's a little more, they're all pretty much the same. They're all pretty simple. All right, so I'll just show you one more. So HBr plus H2O. And then the question is, predict the two products, okay? So again, what you do is you recognize, hey, there's your acid, right? You got the hydrogen with the nonmetal, or the hydrogen with the monatomic ion, right? And then you got your water. So an acid reacting with water, what's going to happen is the hydrogen ion is going to get transferred to the oxygen. So that's going to give you, let me write it this way. I'll write it up here. H plus H2O, that's going to give you H3O plus. And again, the name of that ion, it's a polyatomic ion, is called the hydronium ion. It has another name in different parts of the world, but I'm not going to give you that name because that could get complicated. Okay. And then what's the other product? You just take whatever's left. So you know that's Br minus, right? So again, getting back to that idea of the charges, those are your two ions right there, right? So what happens is that's what's going to be left once you lose the H plus. So we would call that, we call it a bromide ion. Right? That's a bromide ion. So you got the hydronium ion and you got the bromide ion. Those are your two ions on the product side. Again, you're just sort of recognizing that if you have an acid and you have a base. Okay. And let's see, I just want to just make sure. Yeah, those ones, they don't give you any. Okay. All right. Oh, let me just make one little point here right at the end. Strong acid versus weak acid. This is often an issue. So I'm gonna go ahead and take a couple of minutes here. So if you need to leave, feel free. So there are different types of acids which we call strong and weak. And here's how you tell. If you put the acid into water, so let's say you have HNO2. And in the water, so this is before dissolving. And then it's after dissolving. So if after you dissolve, you find that there's still some of the original acid left over. So if you look at that combination after you dissolve it, see how it's got some of the original formula left? That means not all of it reacted with the water. That means only some of it reacted with the water. If that's the case, then it's a weak acid. A weak acid is an acid that when you put it into water, only some of it will break up into H plus and NO2 minus. Okay, so only, some of it did, but not all of it. There's still some of this remaining. So we call that a weak acid. If, on the other hand, the original formula is HNO3, and then after it dissolves, there isn't any HNO3 left over. So you have the H plus and you have the NO3 minus, but there's no HNO3 left over. That means all of it reacted. And that's what a strong acid is. So that tells you right here it's a strong acid. So our strong acid, all of it is ionized. So for example, H plus and NO3 minus in water. A weak acid, only some is ionized. So you get H plus, NO3 minus, NO2 minus, and then you have still some of the original acid left over. So it turns out some acids, when you put them in the water, only some of it will actually react with the water. The rest of it will just remain unreacted. We call them weak acids. They are also weak electrolytes because not all of it's forming ions. They don't conduct electricity very well. Strong acid, all of it reacts with the water. And so 100% of it will get converted into the H plus and the NO3 minus. So if you're given a problem where they show you what occurs after the dissolving, if you see some of the original material, that means it's a weak acid. If you don't see any of the original material, that means it's a strong acid. Okay, and there you go. So that's acid-base chemistry. So try some of those today if you can. And then tomorrow, if you have any questions on them, we can look at them, specific examples. And then what we'll do is we'll move into talking about reduction oxidation chemistry, which is section 4.4. It's actually a pretty rich material. That's all the kind of idea about oxidation and reduction and battery technology and all that stuff. We're not going to go into all of that, but we'll give some introduction into what redox chemistry is. And then on Thursday, we'll look at molarity calculations, and that should wrap up chapter 4. Okay. So very good. Have a great day. Reach out to me if you have any questions, and good luck with everything.
Thank you.
Thank
Have a
you.
great day.
Thank you, Professor.
Take care.